Hello, welcome everybody. My name is Jung-San Kim. I'm a Chief Technology Officer at IonQ. Today, we will have a short presentation on the technical roadmap of IonQ that is supporting the enterprise-grade quantum computers that we're working on opening up today. I am very excited to be joined by two of my outstanding colleagues and technical leaders of the company. Dr. Dean Kasman of Vice President of Engineering at IonQ, and also Dr. Pat Tang, who's Vice President of Research and Development at IonQ. We would like to make sure that you understand there are a lot of forward-looking statements. I'd like to make sure that we take that into consideration. Please make sure that you review this disclaimer as you attend this workshop. I would like to see at high level, what we are focusing on is how to get to a measurable performance with quantum computers. Our goal is to get to quantum computers that are powerful enough to be able to do computational tasks that cannot be simulated or emulated by classical computers. And for that, we need technology development paths that improve our gate fidelity, introduce techniques like error mitigation, that eventually gets to a metric that we have been pursuing called algorithmic qubits, which actually measures how big of a quantum circuit you can actually run in our systems. We also have several technology development items that increase the system size and scale. Very concretely, things like trap technology, how we go from a single core to multi-core quantum processors, and how we eventually network quantum computers build kind of infinitely scalable architecture. And also, it's also very important to realize that once we know how to build these large-scale systems that can do very interesting quantum circuits, we have to be able to deploy this at scale, make sure that people can actually use it. And that actually is another topic of discussions that we'll have today. So more concretely, there are a large number of topics that will be covered by Dr. Kasman and Dr. Tang. And the next slide, you will see that on the on the measurable performance side, we're going to discuss a little bit about the gate fidelities, some of the error mitigation techniques, and the algorithmic qubit numbers that we've been pursuing. In order to make sure that we can build larger and more scalable systems, we're going to talk about trap technology and our multi-core and photonic networking technology. And on the last side, we will discuss some of our new developments in a different qubit species that we've been working on, and how we continue to engineer our systems that are going to be much more manufacturable. With that preamble, let me turn this over to Dr. Dean Kasman, VP of Engineering at IonQ.
Hello, everyone. It's great to be here today and kind of talk about some of the work that we're doing and kind of where we're going. And so I'm going to start by talking about performance and kind of touch on some of the ingredients in terms of both fidelity, some of our kind of error mitigation techniques, as well as our overall approach to kind of application-based benchmarking, kind of in terms of what we need to do to get to AQ64 as well as beyond. And so let's just kind of jump right in. So I want to first talk about fidelity. And so, fidelity is a component level benchmark that measures how well and how good our gates are to ideal. And so, a gate fidelity of 1 would indicate a perfect gate. So we often talk in terms of kind of percentages close to 1, like 99.9%. I'll be talking today also about infidelity or gate error, which is kind of fractions away from 1. So like 100 parts per 10,000 or 0.1%, they all mean the same thing. So why is fidelity important? So as we're executing circuits, we need to string together a series of 1 and 2 qubit gate operations through time to execute. And so no matter how fast your gates are, if you have poor quality gate operations, the probability of an error will continue to grow and you'll get garbage as an answer. So fidelity becomes a critical piece to scaling as well as reaching kind of greater circuit depth, as well as just getting the right answer. Now, in calculating fidelity, we have to take actual physical measurements on the system. And there's different ways to do that. In reality, there's just about as many variations of infidelity that scientists care about as there are ways to measure them. When we say gate fidelity, we refer to the fact that we're measuring entanglement fidelity, and we're using a variant of what's called randomized benchmarking, in particular direct randomized benchmarking, to kind of do that. And so we have a link here to the paper that kind of describes a little bit more about the approach that we're taking. So I want to jump into 1-qubit gate fidelity first. So the 1-qubit gate fidelity measures the performance of our 1-qubit gates. In the data that's shown here is coming from a recent paper that we published on arXiv, but in that particular case, we had Forte configured in a 30-qubit configuration. And so we have 31 qubit gates that we measure, and we report on the median of that. So in our all-to-all architecture, we're looking at the performance across all of the gates and reporting kind of out the median values. Right now, we are operating at roughly 99.98% on a median gate 1-qubit gate fidelity. Now, if we think about 2-qubit gate fidelities, 2-qubit gate fidelities are calculated across every possible combination of pairs in this case, once again, a 30-qubit chain. So that's 435 pairs. As we add more pairs, the number of, or as we add more qubits, the number of pairs increases. And so the number of pairs will increase dramatically as we start to scale. Now, realistically, it's difficult to manage kind of high fidelity operation of just a handful of pairs. To be able to generate system level performance that results in high fidelity kind of circuit execution, there's many things that can kind of impede us. Control system limitations, both electrical as well as in the electronics as well as software, qubit crosstalk, context dependence, or even just overall qubit quality uniformity all affect or contribute to kind of our gate errors. Now, in the plot, you'll see that all of the 2-qubit gate fidelity data is not created equal. There are some more performant pairs where others are not. And so that's why when we talk about the number of ions in our systems, the number of ions is not equal to the number of qubits. And the number of physical qubits does not equal the number of useful qubits that we need to do calculations. And so we have more ions than physical qubits and more physical qubits than algorithmic qubits. And that brings us to our roadmap. And so when we look at where we are now and where we're going, we're using laser light to drive the atomic transitions that are the basis of our gates. They're not all perfect. They're very, very good, but not perfect. And so we form these gates by shaping control pulses. They're essential for high fidelity and stable operation. And so, if we think about the engineering work that we're putting into our systems, we need to deeply understand those error sources and engineer them out. There's two kind of broad classes of work that we're using in this approach. One is diagnostic characterization, and the other is model-based design. So all that points to being able to understand the why behind what we're observing, and then using that information to improve the underlying hardware and software, or in fact, change the way we operate the system. We can even tailor the control pulses to target specific types of errors. And so this represents kind of an engineering iteration loop where we feedback on the learning and push that back into the design process. Now, as we look to scale overall performance, both scale as well as performance, we're going to need to improve component level fidelity. But that's not just for a single pair, it's for all pairs. And so we're going to be orchestrating system level performance through a combination of things. That includes better control system electronics, better optical engineering, better trap development, and better software. These are all things that we're investing in now, as well as into the future for our roadmap. And we hope to be able to kind of cover them in more depth in the future. But if we talk about errors, I want to talk about error mitigation next. The error mitigation allows us to kind of, well, let me back up a second. Improving fidelity focuses on kind of the hardware aspects. It allows us to increase the larger overall kind of circuit width and circuit depth that we can execute and run. Increasing fidelity isn't the only option available to us. In fact, error mitigation techniques are a class of techniques that allow us to kind of remove systematic and some types of stochastic errors in the engineering design. And so as we move to higher performance levels, we're expecting that our 2-qubit gate errors will be the bottleneck. Right now, our 1-qubit gate errors, as well as our spam errors, are under control. And so we know from observation and measurement that our 2-qubit gate errors are generally systematic and coherent, and therefore amenable to these kind of classes of techniques. And so from a philosophy perspective, our approach has been to first design out the errors or the error sources to the extent that we can. And then for those error sources that we can't design out, we then mitigate. And so the error mitigation compensates the errors kind of algorithmically to boost the underlying signal. And so that can be through compiler optimizations or post-processing, and there are other techniques as well. Now, fidelity improvements, as well as these error mitigation techniques, is what kind of allowed us to achieve AQ29 on Forte. Now, the example that's shown here in the slide is an example of a combination of error mitigation techniques called debiasing as well as gate twirling. What they do is rely on the fact that we can remap the original circuit into a new circuit, which should mathematically give the exact same outcome. If the old circuit had cases where there were systematic errors being accumulated, these kind of techniques will end up canceling out the errors on average, and then resulting in a final result that's closer to the true and correct answer. We're using these techniques kind of currently, and we're continuing to invest in these as we move forward. And these are going to be essential as we try to hit, our roadmap milestones of AQ64 and beyond. Now, the error mitigation techniques and the fidelity pieces are not the only story. When we talk about component level benchmarks like fidelity, they're not the only part of customer success. And so we have an overall philosophy that we've taken that application oriented benchmarks, allow us to both characterize the overall full system performance as well as eke out errors and kind of system design aspects that you just would not see at a component level benchmark. And so they really give us integrated machine performance. And they also are intended to reflect kind of real world customer experiences. They're not an absolute representation of customer experience, but what they are is a proxy for workloads that we can expect customers to run. Right now, we have an algorithmic benchmark, an application-oriented benchmark that's been crafted based by the Quantum Economic Development Consortium, QEDC, and it includes benchmarks that are trying to target application areas like optimization, quantum simulation. And so we continue to push on application-oriented benchmarks, and it's a big part of our overall philosophy. And so as we think to kind of now and in the future, they're really driving three different areas. And that is focusing on hardware performance to increase kind of the raw depth and width of the quality of the results that we can get. And so that's primarily through fidelity development. The second, we're investing in the software and compiler optimizations to kind of drive and get, reach as many possible applications as possible through those kind of improvements. And third, investing in error mitigation techniques. And so this is all on our kind of roadmap to error correction. Now, if we think about the scale aspect outside of performance, I'm going to talk about some of our trap development as well as some of our other work as we kind of think about scale. So for traps, let's start by talking about our EGT, our evaporated metal and glass trap. The trap is the core of our quantum computing technology. Lasers are used to ionize atoms flying through vacuum, allowing the atoms, or now ions, to be kind of confined and manipulated by electric fields in the traps. Today, we load our ions sequentially to create a linear ion chain and then move those ions to a quantum zone for operation. Now, the ideal trap technology would be one where we can store, control, and dynamically reconfigure a large number of ions with very high speed, very high accuracy, and precision. Additionally, what we want to be able to do is fabricate them with high yield and uniformity to support, our overall production development. Now, ions are extremely sensitive to stray electric fields from charging, from kind of non-conducting surfaces, and our EGT, we haven't talked about it much in the past, but it uses glass micromachining to form high aspect ratio electrodes that shield those ions from kind of sources of stray kind of electric fields. It also allows us to kind of create high numerical aperture kind of shaping so we have, I would say, high numerical aperture optical beam access to be able to kind of drive all of the beam operations. Right now, optical access is one of the most precious resources we have in our systems, and our traps are designed to be able to kind of drive that. And so the EGT, has been the first in our line of trap technology, and it's what's going into Forte Enterprise. Now, due to the fact that it's single layer technology, it's incompatible with scaling to very large numbers, hundreds of ions, and therefore, we need to invest in the new technology. And that brings us to the MGT. So the multi-layered glass trap technology, or MGT, it relies on standard semiconductor manufacturing processes to easily produce traps at quantities that we need. It also adds signal lines that are below the trap electrodes for more complex kind of trapping architectures. It also allows, and it's been tuned for large scale, right? Multi-chain transport and multi-core. I'll talk about that in just a moment. But the all-metal surface electrodes provides kind of the necessary shielding against kind of stray electric fields. Right now, we do not believe that MGT has any fundamental limit to the number of quantum zones that we can support, because we can simply add more routing layers to be able to kind of drive the necessary electrode configurations. It's also right now in kind of a third generation of development, and it's going to be what we'll be trying to push for in use on AQ64. So overall, the MGT is leveraging all of the lessons that we have from our EGT technology and work. It also leverages kind of high aspect ratio design. It has materials that support low noise operation. It has the high numerical aperture, and there's new semiconductor manufacturing techniques to try to kind of scale with quantity, quality, and yield. So overall, the trap technology is kind of a critical piece as we start to go into our scaling paradigm. And so I want to jump now to kind of our single core and kind of the multi-core aspects of scaling. So a key aspect in single core operation, and that we've talked about quite a bit, is getting that kind of large number of qubits in a single chain, okay? In single core operation, you need precision ion control and placement, as well as high performance beam delivery for state prep, gate operations, as well as readout. Now, the trap design is a key piece of this. It allows us to kind of, like I said, store, control, and dynamically reconfigure kind of the large number of ions with, that speed, accuracy, and precision that we need. But the optical systems are also another important component. In Forte, we introduced the AOD technology to support high precision beam steering. It can easily accommodate different ion spacing across the chains. We've also improved our upstream beam modulations to support kind of better beam quality and stability. The improvements kind of have been accompanied with kind of improvements in our control electronics, and the results of which is basically very high fidelity, all-to-all connectivity, all-to-all connectivity for a single quantum zone. And that's what we have today. As we move now to 2025 in our roadmap and beyond, we're looking to a multi-core architectures. And this is what we've called RMQA. It's the reconfigurable multi-core quantum architecture. And so in RMQA, we're leveraging all the learnings from single core, but now moving to a multi-core capability. In the MGT traps are kind of a key component of this. Like I said, there's no fundamental limit to the number of cores that we can create in the MGT. The zones in the multi-core are completely reconfigurable. They rely on shuttling. Where others shuttle single ions, we shuttle chains in this architecture. Shuttling chains allows us to reduce the overall overhead and kind of performance hit that's induced by shuttling. So shuttling can introduce heating from excess motion. That's solved with refrigerant ions and sympathetic cooling. And so what we have is that activity occurring within each of the zones in the all-to-all configuration, with all of the zones operating in parallel. So that allows us to increase scale without sacrificing fidelity. So one of the advancements that comes with RMQA is not just kind of the trap hardware itself, it's also the software and the compiler. So one of the things is a multi-core compiler that we're developing that can automatically determine how to best kind of take a circuit and decompose it across the different cores in an optimal way with the lowest possible overhead. Another advancement that's going to be coming alongside of multi-core is mid-circuit and partial measurement, but we'll talk about that in the future. I want to turn things over to Pat right now to kind of talk about some of the scaling pieces that we have in place for beyond 2025.
Thank you, Dean. Dean talked about scaling with multiple ion chains. We now move on to scaling beyond AEQ64 with photonic interconnects. So let's go to the next slide. And here we see that the realm of quantum computing beyond AEQ64 will involve an interconnected quantum processor, just as modern CPUs have interconnected cores, even interconnected CPUs. So for us in the quantum world, entanglement ensures that each quantum computing core is correlated and connected as depicted by this correlation diagram on the right. So I want to emphasize that the power of quantum computing lies in these number of interconnections rather than just the number of QPUs or ions themselves. So if we go to the next slide, we'll look at the architecture of our photonic interconnect scheme going beyond AEQ64. You see in the gray rectangle, which is a representation of each ion trap module, is comprised of computational qubits, the gray circle, and the purple qubit, which is our interconnect qubit. These two qubits are entangled, and in this way, information can be transferred between the computational zone and the interconnect qubit. So once this happens, each of these photonic interconnect qubits fire a photon, which are then routed by the photonic switch and eventually meet at the photon interference setup that you see at the top, the top three rectangles here. And here is where the single photons from each module are entangled, which then leads to the connection of the different modules. So in this way, this is how we can achieve a networked quantum computer. So that's the architecture. Let's dive a little bit deeper into the physics in the next slide. So what we have here on the left is an atomic representation of the different states of our interconnect qubit. And you can see that we excite this interconnect qubit first into the P state, and then we allow this electron in P state to spontaneously decay and emit a light photon to two possible S states, represented by the logical 1 and 0, which in physics are spin up, spin down states. So each transition also involves a different polarization of light, which is emitted to conserve energy, pi and sigma polarization. We're blessed in quantum mechanics to allow this decay to be ambiguous, meaning that instead of just producing a pi or sigma polarized light photon, quantum mechanics actually allows this photon to be in a superposition of both the pi and sigma polarization light. So we're going to label this for simplification as the H and V state. So this light, as it comes out of the ion trap, is then focused through optics onto a single mode fiber, and then travels down this fiber as an entangled HV state with the computational states of 1, 0. And this is what we end up with mathematically as the equation on the right. We have a quantum state, which is an entanglement of both the photon polarization with the computational states 1, 0. So on the next slide, we're going to see two photons emanating from two different traps, which meet in the middle of this interference setup that we can see detailed on the right. It has a so-called non-polarizing beam splitter at the center, which is the MPBS, and this mixes the two photons. So by the time it emanates from this beam splitter, you can't tell which photon came from which ion trap as it emerges from the beam splitter and goes towards the green detectors. And so in this way, the photon states from the two different ion traps are entangled, And when they're detected by the green detectors, as we know from quantum mechanics, you destroy the photon entanglement, but then you're left with the electronic entanglements, the ones and zeros between the two different ion trap modules. So this is like a high-level view of how we create entanglement between two different ion trap cores. And this is how we're going to move to our vision in the next slide of our networked QPU here. So this is a kind of visual of what we envision as our networked quantum computer one day. So we've talked a lot about our photonic interconnect scheme. I want to move on and discuss what about the ion species themselves. So here we have a criteria for our qubits and what they must fulfill. Fortunately for us, in the ion trap method, we have qubits which are identical. That makes the physics much easier as we build quantum computing computers. And this is kind of, we're afforded like a luxury which other schemes are not always afforded. They're very stable, and they're stable, and they have long coherence times. And we also really understand the system very well. So ytterbium has been the stable, well understood workhorse, as it were, of our systems. But in the ion trap community, it's not the only ion. There's also barium. It has different isotopes and other benefits as well. Just as technologies have different species, we could talk about semiconductors, we can talk about batteries having different chemistries. The ion trap community also have different ion species, and barium itself also has different isotopes. And there's a particular isotope which lends itself well to a photonic scheme, simply because it has optical transitions in the visible spectrum rather than the UV of ytterbium. And this lends itself well to engineering optics to enable our future quantum computers. So we talked about our ions, and I want to talk a little bit about our architecture moving forward and how we scale from a physical system standpoint. So if we go to the next slide, our current systems are really very custom. They contain optical tables, a lot of custom launch plates for the lasers, large laser systems, a lot of custom optics. And we're moving towards scaling these systems so they can operate in a data center and also put them into like a rack-mounted form factor. So in 2025, in our roadmap, we're going to have Forte Enterprise, which is going to be comprised of a rack-mounted form factor with a 40% reduction in footprint, which will make it more data center friendly. But we're not stopping there, because in order to scale, in order to go to the many different modules, we're going to have a cost down of our systems. So as we move towards 2025, we're going to continue reducing our footprint and also making these components more modular as well. So just in summary, we've covered a lot of ground today. We've talked about how we're scaling our performance. Dean talked about how we're increasing our fidelity from now, and we have targets going to 2025 and 2025 beyond. We talked about AQ and how we're using kind of application-specific metrics to look at the performance of our computers. We're at AQ 29 today, and we recently announced this in our barium systems as well. And we have a goal of going to AQ 64 and beyond in the next few years as well. We also talked about scaling our architecture, moving from single zone Raman to multiple zone Ramans, and also trap technology, which actually scales as well into multi-layers. And then we've also finally talked about in our manufacturing roadmap, how we're moving from really single, very physics-based systems, but thinking about engineering and thinking about making them more modular, decreasing the footprint in 2025 with Forte Enterprise, and moving beyond as we modularize our systems more and make them truly more cost-effective going into this interconnected computing networked era. So we've covered a lot of ground. We look forward to sharing more occasions where we can share the narrative and our technical journey with you. And so this kind of ends the presentation. With that, I'll hand you over back to Nikhil and Trevor. Thank you.
Thank you. Thank you, Pat. And thanks to all our presenters. Of course, you can always learn more about how to get started by visiting our website, ionq.com/getready, and reach out to us. We're happy to answer more questions, talk about our systems, etc.